A remote sector of the southernmost continent has once again drawn global scientific attention after a powerful seismic event rippled through a region long considered isolated and largely stable. Beneath vast stretches of ice and frigid ocean waters, forces that operate far beyond human perception appear to be shifting in ways that are becoming increasingly difficult to ignore. Could a system once believed dormant be reawakening? What mechanisms could sustain tens of thousands of earthquakes in such a short span of time? And what does this renewed activity reveal about the deeper structure of one of the least understood regions on Earth? On March 20th, 2026, at approximately 0202 Coordinated Universal Time, a strong earthquake struck near Elephant Island in the South Shetland Islands. Initial readings placed the magnitude at 7.0 before subsequent revisions adjusted it to the mid-6 range, with different monitoring agencies converging around values between 6.6 and 6.7. While such discrepancies are not uncommon in early seismic analysis, the event still stands as one of the most powerful recorded in this region in more than 5 years. Its relatively shallow depth, measured at roughly 5 kilometers or about 3 miles beneath the seabed, allowed seismic energy to travel efficiently toward the surface, intensifying its geophysical impact. Despite its strength, there was no tsunami threat associated with the earthquake. Monitoring systems across the Pacific confirmed the absence of ocean displacement significant enough to generate hazardous waves. This outcome may appear reassuring on the surface, yet it does little to diminish the importance of the event itself. The true significance lies not in immediate danger, but in the broader pattern it represents. The South Shetland Islands occupy a unique and complex position within the Earth tectonic framework. Located between the Antarctic plate and the Scotia plate, this region is defined by a small but highly active microplate. Measuring roughly 200 kilometers or about 124 miles across, the Shetland microplate exists in a state of constant geological tension. To its northwest lies the South Shetland Trench, a remnant of a once extensive subduction system where one tectonic plate was forced beneath another. To its southeast stretches the Bransfield Strait, an area where the crust is actively pulling apart, creating a back-arc basin characterized by ongoing rifting. This simultaneous exposure to compressional forces from subduction remnants and extensional forces from rifting makes the region exceptionally dynamic. It is not merely one tectonic process at work, but multiple systems interacting within a relatively confined space. The microplate itself formed only a few million years ago, a remarkably short period in geological terms, and its evolution is closely tied to the retreat of the ancient Phoenix Plate. As that plate gradually descended into the mantle, it triggered structural changes that transformed older fault systems into new zones of activity. Within this already intricate environment lies an even more intriguing feature, a submerged volcanic structure known as Orca Seamount. Rising approximately 900 meters, or about 2,950 feet from the seafloor, this underwater volcano became the focal point of intense scientific interest, following an extraordinary sequence of seismic events in 2020. Over a span of just a few months, from late austral winter into early summer, researchers recorded approximately 85,000 earthquakes originating from this single location. Such a concentration of seismic activity over such a short duration is virtually unprecedented in Antarctic observations. The swarm included multiple events exceeding magnitude 6, along with numerous smaller tremors occurring in rapid succession. What made this sequence particularly remarkable was not only its scale, but also the underlying cause. Detailed analysis revealed that the majority of ground deformation observed during this period was not driven by the earthquakes themselves, but by the movement of magma beneath the seafloor. Molten rock forced its way upward through fractures, forming what is known as a magmatic dike. This process displaced the ground surface by approximately 11 centimeters, or about 4.3 inches, a measurable shift that occurred without any confirmed eruption breaking through to the ocean floor. Only a small fraction of this deformation, roughly 4%, was attributed directly to seismic shaking. The overwhelming majority resulted from the slow but powerful intrusion of magma reshaping the subsurface environment. This distinction is critical because it indicates that the seismic swarm was not simply a series of isolated tremors, but part of a larger volcanic process unfolding out of direct sight. Whether Orca Seamount actually erupted during this sequence remains uncertain. The extreme conditions of the Antarctic environment, combined with limited direct observation capabilities beneath the ice-covered waters, make definitive confirmation difficult. However, the evidence strongly suggests that an active magmatic system exists beneath the region, challenging previous assumptions about its dormancy. Since that intense swarm subsided, seismic monitoring has continued to detect ongoing activity. More than 300 earthquakes exceeding magnitude 2 have been recorded in the years that followed, indicating that the system did not return to a completely quiet state. Instead, it appears to have transitioned into a phase of sustained background activity, punctuated by occasional stronger events. The earthquake in March 2026 did not occur in isolation. Less than 6 months earlier, in October 2025, a magnitude 7.6 earthquake struck the Drake Passage just north of the South Shetland Islands. The proximity in both time and location between these two major events raises important questions about regional stress accumulation and release. Patterns like this suggest that the tectonic system may be adjusting in response to deeper structural changes rather than experiencing random, unrelated events. Another notable feature within this region is Deception Island, an active volcanic caldera that forms a near-complete ring with a narrow opening known as Neptune Bellows. This unique formation allows vessels to enter a flooded volcanic interior, a rare phenomenon that underscores the island's geological significance. Deception Island has a well-documented history of eruptions, with significant events occurring in the late 1960s and the early 1970s. These eruptions caused substantial damage to research facilities, demonstrating that Antarctic volcanoes, though remote, are far from inactive. Even in the absence of recent eruptions, Deception Island continues to exhibit signs of activity. Elevated ground temperatures and persistent fumarolic emissions indicate that heat and gases are still being released from beneath the surface. This ongoing activity reinforces the idea that the broader region remains geologically alive, with multiple systems operating simultaneously beneath the ice and ocean. Human presence in this area, though limited, provides valuable observational data. More than a dozen research stations operated by various countries are scattered across the South Shetland Islands. Facilities on King George Island in particular are situated close to the zones of highest seismic activity. Researchers stationed there were among the first to detect the continuous ground shaking that marked the beginning of the 2020 seismic swarm. However, the sparse distribution of monitoring equipment across Antarctica presents a significant challenge. Large areas remain under-instrumented, meaning that many smaller earthquakes go undetected. A focused study conducted over a 3-year period at one station identified more than 1,400 local seismic events, many of which were not included in global earthquake catalogues. This discrepancy suggests that the true level of activity in the region is substantially higher than current records indicate. The implications of these findings extend beyond geology alone. Antarctica plays a crucial role in the global climate system, and interactions between seismic activity and ice stability are an area of growing interest. Vibrations from earthquakes can propagate through ice shelves, potentially accelerating fractures in structures already weakened by warming ocean temperatures. While no direct connection has been established for this specific event, the possibility of such interactions remains an important consideration. As data continues to accumulate, a broader pattern begins to emerge. The South Shetland region is not an isolated anomaly, but part of a wider trend of heightened geological activity observed in multiple parts of the world. From submarine volcanic systems to major fault lines, the Earth appears to be undergoing a period of notable dynamism. What remains unclear is whether these events are linked through deeper planetary processes or simply represent coincidental timing across independent systems. The reactivation of a previously quiet volcanic structure, combined with repeated high-magnitude earthquakes in the same region, suggests that underlying conditions may be shifting in ways that are not yet fully understood. As the sequence of seismic events continues to unfold across the South Shetland region, the accumulation of data is beginning to outline a far more intricate and active system than previously assumed. The persistence of earthquakes following the intense swarm of 2020 suggests that the processes beneath the seafloor did not simply subside, but instead transitioned into a prolonged phase of adjustment. Each tremor, whether minor or significant, represents a release of energy tied to deeper structural changes occurring within the crust and upper mantle. The earthquake recorded in March 2026 adds weight to the interpretation that the region remains under considerable tectonic stress. Its shallow depth, combined with its location near previously active zones, indicates that the forces driving these events are concentrated relatively close to the surface compared to deeper subduction-related earthquakes. This distinction is important because shallow seismic activity is often more closely linked to crustal deformation, fault movement, and volcanic processes rather than distant plate interactions alone. Beneath the Bransfield Strait, the crust is undergoing gradual extension as it continues to pull apart. This rifting process creates fractures and weaknesses that allow magma to move upward from deeper reservoirs. The presence of Orca Seamount within this environment is not coincidental, but rather a direct consequence of these tectonic conditions. As the crust stretches, it reduces pressure on underlying material, making it easier for molten rock to ascend through newly formed pathways. The seismic swarm of 2020 demonstrated how rapidly this system can respond when conditions align. The intrusion of magma during that period did not result in a confirmed eruption, yet it significantly altered the subsurface structure. The displacement measured on nearby landmasses provided clear evidence that large volumes of material had shifted beneath the seafloor. Such movement does not simply reverse or disappear. Instead, it reshapes the stress distribution within the surrounding crust. This redistribution of stress may help explain the continued seismic activity observed in the years that followed. Faults that were previously stable can become reactivated when stress levels change, leading to new sequences of earthquakes. In this context, the March 2026 event may represent part of an ongoing adjustment process rather than an isolated incident. The earlier magnitude 7.6 earthquake in the Drake Passage further supports the idea that the broader region is experiencing a period of heightened tectonic activity. Another factor that contributes to the complexity of this environment is the interaction between different types of fault systems. In many regions, tectonic behavior is dominated by either compressional forces, where plates converge, or extensional forces, where they move apart. The South Shetland area, however, is influenced by both simultaneously. This dual influence creates a network of faults that can respond in unpredictable ways, sometimes producing earthquakes that do not fit neatly into conventional classifications. The presence of active volcanic structures adds an additional layer of uncertainty. Deception Island, with its history of eruptions and ongoing geothermal activity, serves as a visible reminder that magma remains close to the surface in parts of this region. While Orca Seamount is submerged and largely hidden from direct observation, the processes driving its activity are likely similar in nature. The difference lies in the ability to monitor and confirm surface expressions of that activity. Technological limitations continue to restrict the level of detail available from beneath the Antarctic waters. Harsh weather conditions, thick ice coverage, and logistical challenges make it difficult to deploy and maintain monitoring equipment. As a result, much of the current understanding relies on indirect measurements, such as seismic waves and satellite-based observations of ground deformation. While these methods provide valuable insights, they also leave gaps that can only be filled through more direct exploration. Despite these challenges, the growing body of evidence points toward a system that is far from dormant. The concept of a hidden volcano reactivating is not based on a single event, but on a series of observations that collectively indicate sustained activity beneath the seafloor. The combination of frequent earthquakes, ground deformation, and the known presence of molten material suggests that the region is undergoing continuous change. Beyond the immediate geological implications, there are broader considerations related to the stability of the Antarctic environment. Ice shelves in the region are already subject to stress from warming ocean waters and shifting climate patterns. The additional influence of seismic activity introduces another variable that could affect how these massive structures respond over time. Vibrations from earthquakes can travel through ice, potentially accelerating the development of fractures or weakening points of connection within the ice. Although no direct link has been confirmed between recent earthquakes and specific ice shelf events, the possibility of interaction remains an area of active study. Even small changes in ice stability can have far-reaching consequences, particularly when they involve regions that contribute to global sea level balance. Understanding how geological and environmental systems intersect in Antarctica is therefore critical not only for regional analysis, but for global projections as well. The pattern of increased seismicity observed in the South Shetland region also raises questions about whether similar processes may be occurring in other parts of the continent. Antarctica is often perceived as a stable landmass, yet its geological framework includes numerous zones of potential activity. Many of these areas remain poorly studied due to their inaccessibility, meaning that current observations may represent only a fraction of the overall picture. As monitoring efforts gradually expand, it is likely that additional hidden systems will be identified. Each new data set has the potential to refine existing models and reveal previously unrecognized connections between different areas of activity. The challenge lies in integrating this information into a coherent understanding of how the continent behaves as a whole. For now, the South Shetland Islands and the surrounding marine zones remain one of the most closely watched regions in Antarctica. The combination of tectonic complexity, volcanic potential, and ongoing seismic activity makes it a natural focus for continued observation. Every new earthquake adds another piece to a puzzle that is still far from complete. What is becoming increasingly clear is that the processes shaping this region operate on timescales that do not always align with human expectations. Changes that may appear sudden are often the result of gradual build-up over years or even centuries. The events of 2020 and the subsequent earthquakes serve as reminders that even in the most remote and seemingly quiet areas of the planet, dynamic forces are constantly at work beneath the surface. The idea of a hidden volcanic system reactivating beneath Antarctic waters challenges long-held assumptions about the continent. It suggests that there are still significant unknowns in one of the most extensively studied yet least understood environments on Earth. As research continues, each new discovery has the potential to reshape understanding not only of Antarctica, but of the global systems to which it is connected. The broader pattern of geological activity, observed across multiple regions of the world, adds another dimension to this unfolding situation. While each event has its own local causes, the timing and frequency of these events invite further examination. Whether they are part of a larger trend or simply a coincidence remains an open question, one that will require continued observation and analysis to address. For audiences following these developments, the importance lies not in immediate alarm but in awareness. The information emerging from Antarctica contributes to a deeper understanding of how the planet functions as an interconnected system. Each new piece of data helps refine predictions, improve preparedness, and expand knowledge of processes that operate far beyond everyday experience. If you found this video informative and want to stay updated on developments like this, make sure to like, share, and subscribe. Tap that hype icon to help this video reach a wider audience and keep more people informed about the powerful changes happening across our planet.